Today we are going to discuss a very important problem, and this is actually the concept of relativistic equation, which is called Dirac equation. In fact, before this lecture on Dirac equation, I have provided a very short video of 11 minutes on the introduction of this Dirac equation. And in that introductory lecture, I have told you that the half spin particles, that is the particles having a spin half 1 by 2, are described by the first order wave equation. And there are two first order wave equations you have seen in that lecture. The first one is called Dirac equation and the another is Weil equation. Okay. And similarly, you know that when we talk about a particle having zero spin, that very particle can be described by a second order wave equation, and you have learnt in the previous lectures that very important second order differential equation which describes the particles with zero spin, and that is called actually Klein-Gordon equation. Okay. So now in this lecture, we are going to first of all know what is this Dirac equation, okay, and what actually is the prerequisite to know the Dirac equation, and or in other words, you can say what actually was the problem with the Klein-Gordon equation, which was removed by Dirac. You know that there was a very important difficulty with Klein-Gordon equation, that the Klein-Gordon equation was not actually Lorentz invariant, because in that equation the space and time derivatives were actually not of the same order. Okay, and the Hamiltonian was not a linear function of the momentum and energy. Okay, because you have seen that the expression for relativistic Hamiltonian, you know, that is given by H equal to E, and that is equal to a square root of P square C square plus M square C4. And this expression was used in the Klein-Gordon equation, and here you can see that this Hamiltonian and hence this energy is not a linear function of momentum P. Okay, and that's why this equation, the KG equation, was not invariant under the Lorentz transformation. So this was the problem. So Dirac thought how we can use a Hamiltonian which will be actually in fact a linear Hamiltonian in energy and momentum. This was the problem. So let us see how this problem was solved by Dirac. What was the form of Hamiltonian which was used by Dirac to remove this difficulty. Now you have discussed in very detail in my lectures on spatial relativity on the four-dimensional formulation that the momentum 4 vector and the concept of momentum 4 vector. As you know, in quantum mechanics, when you write the momentum operator, that is P hat, that is defined as minus I h bar del. And this may be equivalently written as minus I h bar del del x nu, where nu is equal to 1, 2 or 3, or you also call that this is equal to x, y and z. Okay, and the energy operator E hat, you know, is defined like this, I h bar del del t. In fact, in three-dimensional space, this momentum and energy are treated independently. But when you study the relativistic mechanics, and particularly the 4 momentum vector or momentum 4 vector you can say. In that condition, you know that the momentum 4 vector, which is denoted by the symbol p mu, has 4 components, and those components are p1, p2, p3 and p4. In fact, here this first 3 components p1, p2, p3, these are simply the 3 components of momentum in 3-dimensional Euclidean space. And so instead of this p1, p2, p3, you write p, vector p. Okay? And this 4th component of momentum, that is p4, is recognized as IE over C. So you can see that this energy is nothing. This is simply the 4th component of this 4 momentum vector. Okay? And at the same time, the position 4 vector or the radius 4 vector x mu has 4 components, and those are x1, x2, x3, x4. And here also these x1, x2, x3, these are actually the 3 position coordinate of the Cartesian coordinate system. And the 4th component of this position 4 vector is equal to ICT. All these things you have studied in very detail in my lectures on the 4 vector in the playlist of spatial relativity. Okay. So you can see that these 2 equations which I have written in equation number 1, that is for the momentum operator and the energy operator. Now these 2 operators may be coined, may be casted into a single equation in terms of the momentum 4 vector. You can easily write it. And what will be that operator equation for the momentum 4 vector? You can see that if you denote the momentum 4 vector operator in this form, this is in fact p mu hat. But here don't write the vector sign, because now this is actually the 4 vector, so it will be not appropriate for writing this vector sign. Okay, so this is p mu, and this can be written as minus I h bar del x mu. X mu is here actually the 4 momentum coordinates. Okay, here mu equal to 1, 2, 3 and 4. Okay, and in this condition, you know, when you will substitute the values of x mu, that is x1, x2, x3, you will get the momentum vector p, and when the 4th component of x mu will be substituted, then you will get actually the energy operator. In fact, substituting mu equal to 1, 2, 3, you will get this operator p hat, and when you will substitute x4, then you will get this energy operator E hat, which is equal to I h bar del t. So I have told you that these 2 operator equations may be casted into a single equation by this equation number 2. Okay. Now it is clear from this equation that a first order wave equation requires a Hamiltonian that is linear in momentum vector. Okay. What I have told you, that any first order wave equation needs a Hamiltonian which is linear in the momentum vector. Okay. And in Klein-Gordon equation there was a problem that the Hamiltonian was not in fact a Hamiltonian was not linear in momentum, because you have seen that expression for relativistic Hamiltonian contains the p squared terms. Okay. So in to find a Hamiltonian which is in fact linear in momentum vector, Dirac postulated that the Hamiltonian of a free particle may be defined like this: h hat equal to c times alpha hat dot p plus beta mc square. You can see in this case this Hamiltonian is a linear function of this p, or you can say this Hamiltonian is linearly related with the momentum vector p. In fact, here these operators alpha hat and this beta hat are actually not known at present. These are unknown, but you should postulate that these operators alpha hat and beta hat are independent of this momentum vector p, and these are also independent of space and time coordinate. For a time being, you should assume it. Okay. At the end of this lecture, when we will actually obtain the Dirac equation, then we will find what are actually the meaning of these two operators and what are the important properties of these operators alpha hat and beta hat, and from that property you will conclude that what should be the form of these operators and what should not be the form of these operators. We will find it at the end of this lecture. Okay. So you can see this is just a postulate of Dirac that the aim was to express the Hamiltonian of a free particle as a linear function of momentum, and for that Dirac postulated that Hamiltonian of the free particle may be written like this. Okay. As you know that Hamiltonian or relativistic Hamiltonian, which was used in the Klein-Gordon equation, that was actually of the form like this. This was a square root of c square p square and plus m square c4. Okay, m square c4. And the problem was that in this case the Hamiltonian is not linearly dependent of p, and as it is not linearly dependent of p, so you cannot find the first order wave equation. From this expression you can find the second order wave equation. Okay, but here our aim is to find the first order wave equation, and so in the light of this equation Dirac postulated that when we will write the quantum mechanical equivalent of Hamiltonian quantum mechanical equivalent of this expression for Hamiltonian, and particularly in the view that the Hamiltonian should be a linear function of p, then he assumed that Hamiltonian can be expressed like this: c times alpha dot p plus beta mc square. I am not saying you had for the operator. When I say alpha, you should note that this is alpha hat. When I will told you p, you should note that this is p hat. Okay, and when I will tell beta, you should note that this is beta hat. So there is no need to always pronounce hat symbol. So it will be sufficient to say alpha, p, beta, and you have to understand that these are operators denoted by these hat symbols. Okay. And as I have told you that in this expression the two operators alpha and beta have been used, but the meaning, actual meaning of these two operators are not known till now. Only you can postulate that these two operators are independent of the momentum p, and they are also independent of space and time coordinate. Okay, so this is this expression for the Hamiltonian, which actually represents that the Hamiltonian is linearly related with the momentum vector p. This is actually called the Dirac Hamiltonian, or you can say that this is the expression for Dirac Hamiltonian. Okay. Now actually Dirac found the wave equation by starting with the Schrodinger's time dependent equation. You can see this is actually Schrodinger's time dependent equation. H hat operated on psi of RT equal to I H bar del psi of RT del T. This is nothing, this is simply the Schrodinger time dependent equation. Okay. Now to get Dirac equation, we will simply substitute the expression for the Dirac Hamiltonian in this equation. So if you recognize this Hamiltonian H hat as Dirac Hamiltonian, what you will do? We will simply substitute the expression for this Hamiltonian H hat which was postulated by Dirac, which is called Dirac Hamiltonian. So let us substitute it. You have seen that this Dirac Hamiltonian is defined by like this. This is C times alpha dot P plus beta MC square. Okay, and this is operated on psi of RT, and RHS of equation 4 is at each. This is IH bar del psi of RT del T. Okay. Now, if you will write the operators corresponding to this momentum operator P hat, what will be your result? You know that this momentum operator, is given by what? This is minus IH bar del. Okay. So instead of this operator P hat, I have written here minus IH bar del. So this first term will be minus IH bar C alpha dot del operated on psi plus beta MC square psi equal to IH bar del T psi. Actually here this del T operator is also written as del T. This is just a technique of writing this operator in brief. So instead of del T, you may write the symbol simply del T. Okay. In fact, this equation 5, this is nothing. This is simply the Schrodinger time dependent equation. Only this form of Hamiltonian, which was postulated by Dirac for the linear dependence of Hamiltonian on momentum vector, is substituted here. And after this substitution, this equation is resulted, which is a wave equation of first order, and this equation 5 or this equation 6, you can say, are actually known as Dirac equation. So you can think this Dirac equation can be derived only in 2 steps. There is no derivation. There is no derivation of Dirac equation. This is simply the Schrodinger time dependent equation, and only you have to substitute the expression for this Hamiltonian which was postulated by Dirac. But what is the actual meaning of these operators alpha hat and beta hat? We will now see. In fact, alpha hat is a vector operator and this beta hat is a scalar operator. Okay. But what are the important properties of these two operators? We will now see. Okay. So now for the identification of these two operators alpha hat and beta hat, let us write this Dirac equation which I have mentioned here in this equation 5 in this form, that this RHS, RHS in RHS IH bar del T actually represents the energy operator. Okay, this is energy operator. So instead of this IH bar del T, which represents energy operator, now we will write the energy operator E hat. So writing that operator equal to here, actually that this E hat is equal to IH bar del T. Okay. So that equation 5 can be now written like this. This is C times alpha dot P plus beta MC square psi equal to E psi. I am not pronouncing hat symbol. I only say E, but you have to understand this is E hat. Okay. Now take these two terms in LHS in RHS. Sign will be just inverted, and your result will be what? This will be E hat minus C alpha dot P minus beta MC square psi equal to 0. Okay. This is Dirac equation. Okay. Now, to get the properties of these two operators alpha hat and beta hat, you have to remember a mathematical step. In fact, we simply operate this operator E hat plus C alpha dot P plus beta MC square. Remember, E plus C alpha dot P plus beta MC square. We will operate this operator on this equation 7 from left. Okay. So see here. This operator E hat plus C alpha dot P plus beta MC square, this has been written here, and this is operated on this equation 7, and equation 7 is this much. This is E hat minus C alpha dot P minus beta MC square psi, and that will be equal to 0. Okay. Now this equation can be written like this. This is E hat plus C alpha dot P plus beta MC square operated on what? This is E hat minus C alpha dot P plus beta MC square. I have actually taken here this minus as a common factor. Okay. Now operate this first operator E plus C alpha dot P plus beta MC square on E minus C alpha dot P plus beta MC square. Operate this. This is just in the form of A plus B times A minus B. And you know, A plus B times A minus B, that is A square minus B square. At the place of A here there is E hat, and at the place of B there is C alpha dot P plus beta MC square. So we can write this expression in that manner. You can see I have written it here in that fashion. This is E hat square minus C alpha dot P plus beta MC square whole square psi equal to 0. Okay. Now when we will simplify it, you can see this E hat square is at is, and C alpha dot P plus beta MC square whole square. What will be this? This will be when C alpha dot P will be operated on C alpha dot P. That will be C square alpha dot P square. And plus beta MC square will be operated on beta MC square. That will be actually beta square M square C4. Since here is minus, so all terms inside this bracket will be negative. So I have written here minus beta square M square C4. Okay. Now we will operate this C alpha dot P on this beta MC square. Remember here, alpha dot P and beta hat, these are operators. So you have to maintain the order. Okay. If x times y is written as y times x, that is correct. But if x times x hat times y hat x hat, if these are operators, then this may or may not be equal, you know. So order must be followed here. So first of all, we will operate this C alpha dot P on beta MC square. So this will be what? This will be MCQ. These are actually the scalar multiplicative factor. So write first of all it. And alpha dot P will be operated on beta. Okay. Now this beta MC square will be operated on C alpha dot P. Okay. Just reverse. So this will be MC cube beta hat alpha dot P. Okay. So remember, don't square it just like A plus B whole square, because these are operators. So order has been maintained. Okay. Now, as you know, this alpha hat is a vector operator. So in Cartesian coordinate, you can write it in terms of the operators associated with its Cartesian components. So alpha hat can be written as alpha xi plus alpha yj plus alpha zk. And similarly, this momentum operator p hat can be written as px hat I plus py hat j plus pz hat k. Okay. And so this alpha dot p, what will be this? Okay. You know, in a scalar product, the similar quantities are non-zero and all other quantities are zero. So this will be simply alpha x px plus alpha y py plus alpha z pz. And in fact, in brief, you can write this expression in this manner. This is summation alpha I pi, where I means x, y, z. X, y, z. Okay. Now, this value of alpha dot p, which is equal to this much, now let us substitute it in this equation number 8. So here, which I am just marking by this dot symbol, and here there is alpha dot p, here is also alpha dot p, and here is also alpha dot p. So there will be a lot of algebra, you can see, and instead of these alpha dot p, we will write this expression alpha px, alpha x px plus alpha y py plus alpha z pz. Okay. So see here, this will be E hat square minus C square alpha dot p whole square. And instead of alpha dot p, we will write this much. This is alpha x px plus alpha y py plus alpha z pz whole square. Okay. Minus there is beta hat square m square c4. This is at each, you can see. Okay. Then there is mc cube times alpha dot p. So mc cube and instead of alpha dot p, again we will write this much. Okay. And there is beta hat here, you can see. Now the next term is mc cube beta hat alpha dot p. So this is mc cube beta hat alpha dot p, and instead of alpha dot p, we will again write alpha x px plus alpha y py plus alpha z pz operated on psi equal to 0. Okay. Now this is the equation which we have obtained after substituting the value of alpha dot p. Now we will actually simplify this equation a little bit. You can see, when you will simplify it, the result will be like this: E hat square C square times alpha x square px square plus alpha y square py square plus alpha z square pz square. Okay. Plus alpha x alpha y plus alpha y alpha x times px py plus alpha y alpha z alpha y plus py times py pz plus alpha z alpha x plus alpha x alpha z pz px. Okay. And c square is as a multiplicative factor here, you can see. In fact, here this alpha x px plus alpha y py plus alpha z pz whole square is here, and this whole square has been simplified. Okay. Now the next term is beta square m square c4. Beta square m square c4. So this is at ease, you can see here. Then the another term is what? This is minus mc cube this much. See here. Okay. The page has been turned. but this will be just okay, don't worry. Okay, now see, the result is mc cube alpha x px plus alpha y py plus alpha z pz beta. Okay, so this is minus mc cube this much. That has been simplified to a little bit. Okay, and plus this much. So this last term has been also simplified. Here there is mc cube, here is also mc cube, and here alpha x px beta, alpha y py beta, alpha z pz beta, and in this term there will be minus in fact beta alpha x px, alpha beta alpha y py, beta alpha z pz. Okay, and therefore after simplification you get this result. So there was a lot of algebra and you can do it easily. This is a simple algebra. Okay, so this is the form of the Dirac equation in terms of the components of the operators alpha and p. Okay, now you have studied in the previous lecture the Klein-Gordon equation. You know the Klein-Gordon equation is simply given by e square minus c square p square minus m square c4 psi equal to 0. And instead of this p square, I have written here px square plus py square plus pz square. This is simply the Klein-Gordon equation. Now, since equation 10 is also a relativistic wave equation and equation 11 is also a relativistic wave equation, so we may compare these two equations. So comparing these two equations term by term, you can see at the place of this e hat square there is e hat square, so you get nothing from this term. But the coefficient of c square in this equation 11 is px square plus py square plus pz square, and in equation 10 these coefficients the coefficient of c square are this much. Okay, so you can see here there is alpha x square px square plus alpha y square py square plus alpha z square pz square. Okay, but here there is only px square py square pz square. So it means definitely this alpha x square and alpha y square and alpha z square is equal to 1. I have written here 1 hat. This is unitary operator because this I have written in operator form. If you will not write it in operator form, you will write alpha, then alpha x square, alpha y square, alpha z square. This can also be written like 1. But I have written it in operator form, so I have written here 1 hat. This is unitary operator. Okay, and again you can see that this beta square here is beta square m square c4, but in this equation there is only m square c4. So at the place of beta square there is 1 in this KG equation. So we can compare these two equations and we will get that this beta hat square equal to also 1. Okay, alpha x square, alpha y square, alpha z square and beta hat square, all these are equal to 1. So a square of these two operators, these 4 operators, not 2 operators, alpha x, alpha y, alpha z and beta is equal to 1. This is a very important property. And we will express this property in a very brief form. We will see later. Now, again, you can see that the terms like this alpha x, alpha y, alpha x, okay, and alpha y, alpha z, alpha z, alpha y times py pz, alpha z, alpha x plus alpha x, alpha z times pz px. Such terms are not present in this Klein-Gordon equation. What does it mean? It means the coefficient of these px, py, pz, this coefficient of this px times py, py, pz and pz, px, that must be equal to 0, because such terms are not present in this equation number 11. So comparing term by term, you can conclude that this alpha x, alpha y plus alpha y, alpha x, this will be equal to 0. And similarly, alpha y, alpha z plus alpha z, alpha y is also equal to 0. Alpha z, alpha x plus alpha x, alpha z is also equal to 0. Okay. Now, you can again see these terms. Where I have written it, this is alpha x beta plus beta alpha x px, alpha y beta plus beta alpha y py, alpha z beta plus beta alpha z pz. Like these terms, there is no term present in the Klein-Gordon equation. So definitely these terms will be also equal to 0. Okay, these terms will be also 0 because these are not present in Klein-Gordon equation. So we can write that alpha x beta plus beta alpha x, this is equal to 0. Alpha y beta plus beta alpha y, this is also equal to 0. Alpha z beta plus beta alpha z, this is also equal to 0. Okay. Now, as I have told you that the property which I have mentioned here in this equation 1, where the square of the operator alpha x, alpha y and alpha z has been defined, that these are actually the unitary operator, its value is equal to in fact 1, or its eigenvalue you can say equal to 1. And these equations, these three equations which I have mentioned, this property number 3. Actually, the properties defined in equation 1, the properties defined in 1 and 3 can be written in brief like this. You can write it alpha I, alpha j plus alpha j, alpha I. And you know that alpha I, alpha j plus alpha j, alpha I, this is what? This is anti-commutator of alpha I with alpha j. When you write these operators inside this curly bracket, that means anti-commutator. Commutator is denoted by the symbol a square bracket, but this curly bracket represents the anti-commutator. Okay. And you can see these this anti-commutator of alpha I and alpha j can be written as 2 delta ij hat, where actually this delta ij is what? You know, delta ij is actually Kronecker delta. This is Kronecker delta, you know. And this has been also written in the operator form. Here I and j means x, y, z or 1, 2, 3. Okay. And you know that this Kronecker delta is equal to 1, or you can say when we treat like it as an operator, then we say that it is equal to unitary operator 1 hat when I is equal to j, and it is equal to 0, or you can say 0 hat if I is not equal to j. So you can check that if if we consider that I is equal to j, okay, I is equal to j, then what will be this expression? You can see this will be alpha I times alpha I plus alpha I times alpha I. I am taking that I is equal to j, and that is equal to 2 delta I. Okay, 2 delta II. Write here the sign of hat. So this will be what? This is simply 2 alpha I hat square. Okay, alpha I square plus alpha I square. This is 2 alpha I hat square, and this is 2 delta II. Okay, now this 2 and 2 will cancel out, and you can see that this alpha I square is equal to delta II. But you know, when I is equal to j, then this is equal to 1. So this will be equal to 1. And I is means x, y and z. So you can say that this alpha x square plus alpha x square, alpha y square and alpha z square, all these are equal to 1. Okay. So I have told you that the square of these three operators is equal to 1. And again you can check if I and j are not equal, then you know that this Kronecker delta will be 0. So then these three results you will get. Okay. When I is not equal to j, then these three results you will get. And then we simply say that this alpha x and alpha, you can say that this alpha I and alpha j anti-commute with one another when I is not equal to j. This is actually called anti-commutator. You know, this is called anti-commutator. Okay. Now see this these properties which I have mentioned in number 4. Here actually you can also see that this is also the expression for anti-commutator. Actually all these three relations can be written like this: alpha k beta plus beta alpha k, that will be equal to 0. That will be equal to 0. Or you can say that anti-commutator of alpha k with beta is equal to 0. It means alpha k, here k is actually equal to x, y, z or 1, 2, 3. So you can say that this alpha k also anti-commutes with beta. This does not commute with beta, okay, but anti-commute. Okay. So in fact, you have seen from the properties of these operators alpha and beta that these operators are independent of space and time, as space and time coordinates, as I have told you earlier. And also you have seen here just now that they satisfy the anti-commutation relationship. You have seen that this alpha k also anti-commute with beta, and any two alpha also commutes with one another. So these two properties, that is the alpha and beta, are independent of space and time coordinate, and at the same time they anti-commute. Actually these two facts indicates that these operators cannot be represented by any algebraic number, and at the same time these operators cannot be differential operator. How you can say that these are not numbers and differential operator? You have to say that since the operators alpha hat and beta hat are independent of space and time coordinate, and at the same time they also anti-commute with one another. So these two property is sufficient condition to say that these operators cannot be algebraic numbers and cannot be differential operators. Then what will be that? What will be these operators? In fact, in this condition, we simply say that the representation of these operators as matrices will be the most suitable representation. So actually this alpha and beta are represented in the form of matrix, and these are called Dirac matrices. Actually, in the next lecture on Dirac equation, we will see the covariant form of Dirac equation, and when we will discuss the covariant form, that means the Dirac equation in which these operators alpha and beta will be not treated as an operator, but they will be treated like matrices, which are called Dirac matrices. And then then we will introduce a new operator in terms of this alpha and beta, and we will get a particular form of Dirac equation which is called the covariant form of Dirac equation. So the subject matter of our next lecture on Dirac equation is what? That is simply the covariant form of Dirac equation, and we will also discuss these Dirac matrices alpha and beta. That is, alpha and beta will be treated like matrices. Okay. So I hope you have enjoyed this lecture on this Dirac equation, and this was a very simple concept but very important, much useful for you. So definitely you should watch the video seriously, write down these facts in your notebook. Everything will be clear, and in any examination, either subjective or objective, you will be able to write the answer based on this concept. Okay, it is my hope, and I hope that you have definitely enjoyed this lecture.